Hey everyone, in this video we're going to cover section 7.3 from our textbook, which is confidence intervals for the standard deviation and variance. And so just a little recap of what we've done in the last two sections, which is we did a confidence interval in section 7.1 for the population proportion. And so the population parameter being the proportion, and we used the sample p hat to create that confidence interval. So the sample proportion, and then with our margin of error being the critical value looking up at the z-scores table times the square root of the p hat q hat over n. And then in section 7.2 we did a confidence interval for a population mean, and so the population mean being the parameter and the sample mean being our point estimate. And when we know the population standard deviation, then we continue to use the z-scores table. But when we don't know the standard deviation for the population, we use S as our sample or sample standard deviation, and we also, for our critical values, we use the t distribution instead of the z table for the normal proportion. New in this section, in section 7.3, we're going to estimate a confidence interval for the population variance, so sigma squared, and standard deviation, sigma. So in this case, we don't know sigma at all, and so we don't know the standard deviation or the variance. So when we have large samples, we can assume normal distribution or bell shape. We can find these confidence intervals using a chi-square distribution. So chi, the Greek letter, it kind of looks like a capital X, but with one of the legs is kind of squiggly. And so these are going to be our confidence intervals. For the variance is this formula, and for the standard deviation, you can think about just the confidence interval for the variance, but just take the square root of everything. And so these are going to be our confidence intervals. So those are the formulas. So it's a little bit different than saying our sample minus the margin of error and our sample plus the margin of error as we did before. Now we're going to be using these particular formulas. So let's talk about what those mean. So our critical values are the chi-square left and chi-square right. And for finding these confidence intervals for standard deviation and variance, we have to ensure, just as before though, that we have a simple random sample. Now remember, simple random sample means that the sample has the same probability of being chosen as any other sample of the same size from the same population. So that's what a simple random sample means. And the population must have a normally distributed values. And so either sometimes you'll be told the data is coming from a normally distributed population. In this case, the requirement to be normal is much stricter, because if we don't have a normal population, then we have a risk of larger errors occurring in our estimation. So we're going to revisit our example of the sleepless nights, the sleep survey that you took in Canvas. And so we're going to try to estimate the standard deviation and the variance for the population being American River College students. So, but before we tackle that example, let's really talk about what is a chi-square distribution and what do these values mean. So the chi-square distribution, we use it to construct confidence intervals for variance and standard deviation. So the variable being recorded, so whatever your variable x is, follows a normal distribution, and so the chi-square becomes this kind of like a z-score, but it's a chi-score. Now, in order to see the shape of this distribution, it requires a little bit of calculus, and so this formula is essentially giving you the shape of the curve. And I kind of put the shape out here, and we'll talk about what that means. But so this is our chi-square, and for samples of any size greater than 1. So you have to have at least one data value in the sample, but obviously we want to have at least 30 or more to be precise, and anything, I mean, you definitely want to have more than one data value in your sample. So properties of the chi-square distribution. All chi-square values are greater than or equal to 0, and that's because notice here everything is square. So n, it says for n greater than 1, so when you have n minus 1 here, this is going to be positive number. So everything here is positive, so you don't have any negatives. So back over here with the z-scores, remember you could have negatives in the normal distribution. And in the t-distribution with the chi-square, there are no negatives. Everything is positive. The chi-square distribution is a family of curves determined by the degrees of freedom, really determined by the size of the sample. And same as with the t-distribution, the degrees of freedom are n minus 1. So this accounts for variability from sample to sample. The total area under the chi-square distribution is 1. This is still representing the probability of something happening. So the area under the curve is the total probability distribution. So it should still be equal to 1, just like the normal distribution in any probability distribution. The area under the curve is 1. The chi-square distribution is skewed right, so it's not symmetric like the bell-shaped curve. And the chi-square distribution differs based on the size of the sample, which then affects the degrees of freedom. Right? N minus 1 is the degrees of freedom. So here are examples of shapes of the curve as the sample size increase, right? As our degrees of freedom increase. And so for degrees of freedom 10, that means our sample size is 11. So this is what it looks like. But notice as you get closer to 30, so the size of the sample will then be 31. Notice that now we have more of a normal bell-shaped graph, which it's why a lot of times we ask for samples that are 30 or more, and then we can apply the central limit theorem, which says that once you have samples, the sample size is more than 30, your probability distribution approximates a normal distribution. And so we saw that with the t-distribution, and now we're seeing this with the chi-square distribution. So this, right, because we don't have the positive and the negative, everything is positive, our two critical values are the critical values on the right tail of the graph and then the left tail of the graph. And so this is how we're going to find them. So the value chi-square r represents the right tail critical value. So that's this one, which gives us the area, the blue area. It always gives us the area to the right of the value. So that's our alpha over 2, depending on the level of confidence that we want. And the value chi-square left, L for left, represents the left tail critical value. So that's this one. And that is, so the area to the right of the curve is your 1 minus alpha over 2. Now notice that the area to the left will still be your alpha over 2. So those are our critical values. So let's do an example finding those critical values. So this one, find the critical values, the chi-square right and chi-square left for a 95% confidence interval when the sample size is 18. So first we're going to find our degrees of freedom. So 18 minus 1 is 17. Next we're going to find our chi-square left and chi-square right using the table in our textbook. So we look for the area to the right to be 1 minus alpha over 2. So what this means is, so 95% confidence. So what is alpha? So with 95% confidence for a confidence interval, we're going to say then alpha is 0.95, 1 minus 0.95. Right, so essentially our C, the confidence, is 0.95. So convert your percent to decimal, and then alpha is 1 minus C, so 1 minus 0.95. So that means alpha is 0.05, and then alpha over 2 is 0.025. So we're going to look at, so for chi-square L, we look for the area to the right of 1 minus alpha over 2. So 1 minus 0.025 is 0.975. So that's what we're going to look for. And for chi-square right, we're going to look for the area to the right of just alpha over 2, so just 0.025. And so we're going to go to our textbook. So from our canvas, go to My Lab and log on to My Lab and then hit on or click on the e-text. And once you're here, you're going to go to the table of contents. And unfortunately, we can't do what we were doing before to go to z-scores and t-values because we want the chi-square table. So you're going to go to Appendix A, Tables, and we're going to look for our chi-square table. And so you're going to have to scroll to the different pages until you get to the chi-square. So that's our negative z-scores, positive z-scores. You'll get to the t-distribution, and right after the t-distribution is our chi-square distribution table. So this is the one that we want. And so looking back at our values, so I want degrees of freedom to be 17 and then 0.975 and 0.025 are the areas that we're looking at. And so when we go back to our table, we're going to have, okay, so here's my 0.975 and here's my 0.025, but I need to be with degrees of freedom 17. So it's right here. So I copied our table onto here, and so here is degrees of freedom 17, and we want 0.975, so this will be our left tail critical value, and then 0.025 and degrees of freedom 17, so 30.191. So those are our two values, so the left tail and the right tail critical values. And so let's write those down over here. So that means that our x chi-square left is, what did we say it was? The one I highlighted, 7.564. So let me write it over here. So this is my chi-square left, 7.564, and then my chi-square right is the 30.191. And so that's how you find them using the chi-square table. So look at the areas up here based on the level of confidence, and then or level of significance, and then go to your degrees of freedom and find where they meet up. Let's go back to our notes. And so here's the graph. So this is what it looks like. So there's our left critical value, 7.564, and there's our right critical value, 30.191. So we have our alpha over 2, 0.025, and this is what I was saying too. That's also alpha over 2, and then the middle in between those is your 95%, the 0.95. Now to construct a confidence interval, we'll need to find those values and then use the formula that I gave you up here for the variance is this formula. So there's our critical values, and then for the confidence interval, you just find the confidence interval for variance, take the square root to find the confidence interval for the standard deviation. And so let's do that for the sleepless nights example. So this is just some notation just to remind ourselves. Sigma, the population standard deviation, so that's the parameter, population variance parameter. And then once you hit samples, those are statistics. So a statistic is S, the sample standard deviation. Another statistic is S squared, the sample variance. The size of the sample is N. The margin of error is our chi-square. And then the left tail critical value, and then the right tail critical value. And here are our formulas again for confidence interval for the variance and confidence interval for the standard deviation. So in our sleepless nights and the sleep survey that you guys took, let's revisit that and let's find a 95% confidence interval for the variance. So let's go back to StatCrunch or to our previous notes to get the size of the sample, the mean, and the standard deviation. So log on to StatCrunch and find that information and then bring it back over here. The sample standard deviation is what we'll use. We need it here to find the variance All right, so from StatCrunch, we know that the sample size was 39, the sample mean was 7.372, and the sample standard deviation was 1.521. So based on the sample data, what is the point estimate for approximating sigma square? So this is the population variance. So our point estimate for the variance will be the sample variance, so S square. And then our point estimate for the standard deviation, the population standard deviation, is the sample standard deviation. So does our sample meet the requirements to approximate the population variance? So the requirements are it has to come from a population that is normally distributed, which when we did this example last time, we did have that assumption that the population of ARC students was normally distributed in terms of the hours of sleep from the previous night. But also notice that our sample size is 39, which is more than 30. So the central limit theorem applies. So we can say that in here. Now, using a 95% level of confidence, find a confidence interval for the variance. So that means that we have to find, what do we have to find? Our critical values, the chi-square left and chi-square right, based on the confidence level. So it is a 95% level of confidence, so we can use the values. Can we use the same values as before? So in the prior example, we had 7.564 and 30.191. No, right? Because our sample size is different. So our degrees of freedom are going to be different. We're going to be looking at the same columns, but our degrees of freedom are going to be different because our sample size is now 39. So we need to first then find the degrees of freedom, and then our point estimate, and then the critical values. So let's do that. So I'm going to reduce some of the same work that we already did, but just to make sure that we understand what's happening. So based on the confidence level, since it's 95%, then alpha is 1 minus 0.95, which is 0.05. So then alpha over 2 is 0.025. Right? So then when I look at I need to look at my chi-square left and my chi-square right for these alpha over 2 value, and we need to find our degrees of freedom. So degrees of freedom are 39 minus 1, so 38, and so I need to look up the area of 0.025. So areas to look are the alpha over 2 and 1 minus alpha over 2. So 0.025 and 0.975. So let's go back to the table and let's find for degrees of freedom 38 these two columns. So going back to the textbook, here is our table, and let's find our degrees of freedom. So I'm going to go to 38, and it goes from 30 to 40. So what do? We round down. Always round down. This is looking up the size of the sample, right? So we don't want to say oh 40, because now you're adding extra values that we don't actually have. So it's always best to round down. We're already saying our degrees of freedom are n minus 1. We're throwing out a value to accommodate for variability from sample to sample. So it's best to always round down. So now we're throwing out 9 values, and we're going to use those. So let's see. So 0.975, so that's the third from the right, or from the left, and then third from the right. So those columns in with 30. So 16.791 and 1, 2, 3, and 46.979. So those are going to be our critical values. So the left is 16.791 and the right is 46.979. So let's go back to our notes. So our chi-square left was 16 46.791, and our chi-square right is 46.979. So those are the values that we need, and now we can compute our confidence interval. Give myself more room here, and so let's bring in the formula. Since we're trying to find the confidence interval for the variance, we're going to use this formula. And so now let's see. So n minus 1, so we already have that. That's our degrees of freedom. So that's 38. So I'm going to have 38 times s squared. Now our point estimate was the standard deviation square. So 1.521 square. So I'm going to put that in here. Over chi-square right. So be careful, even though this is the left side, we use chi-square right. So the 46.979, that's less than our population variance, less than, and then the same thing here, 38, 1.521 squared, but now over here on the right is by chi-square left, so 16.791. And so when we put this on our calculators, what do we get? So the nice thing is that the numerators are the same. So then once we put this all together, we're going to get 1.871 for sigma squared and 5.235. I'm rounding to 3 decimal places, but pay attention on your homework. What are you being asked to round to? If you're not told, assume 3 decimal places. So then this is our confidence interval for the variance. So that means this is a 95% confidence interval for the variance. So that means we're 95% confidence that the population variance for hours of sleep by ARC students on a typical night is between 1.871 and 5.235. Now if I wanted for the standard deviation, then I just take the square root of this. Right, so then that gives me the confidence, 95% confidence interval for the population standard deviation. Interpret your confidence intervals. That means you are 95% confident that what is between what two values. So we are 95% confident that the population variance is between 1.871 and 5.235. So that's how you will interpret that. You can also interpret in the context of the problem. As we get into more hypothesis testing, we'll practice more putting it in context. So the next part is, what if we wanted to increase or decrease our level of confidence and say find a 90% confidence interval? What would change? So if I want to find a 90% confidence interval, this will stay the same, but now I need new chi-square values. So I will find my alpha will be a little different, right? My C will now be 0.90. Alpha will be 1 minus 0.90, which will be 0.10, and then divided by 2. And then find your alpha over 2 and your 1 minus alpha over 2 for those new areas, and that will give you the new chi-square left and chi-square right. And then replace those values here. So try that on your own and then submit it with your notes and see what you get for your 90% confidence interval. What do you expect it to be, by the way? Wider than this interval, than the 95 for variance? You're doing it for variance. Wider than the variance confidence interval of 95% or narrower? So include that in your notes when you submit them. And contact me if you have any questions.